The photoelectric effect is one of the most important discoveries in modern science because it reveals how light can be transformed directly into electricity and explains why solar panels work the way they do. To understand it clearly, imagine a metal surface packed with electrons that are loosely held by the atoms inside the material. When light shines on this surface, you might expect brighter light to simply heat it up, but something far more interesting happens. If the light contains enough energy, it can knock electrons out of the metal entirely, creating an electrical current. This strange behavior puzzled scientists for years, because classical physics predicted that any bright enough light, no matter the color, should eject electrons as long as the intensity was high. But experiments showed the opposite. Even very intense red or yellow light failed to release electrons, while weak ultraviolet light easily knocked them out. The breakthrough came with Albert Einstein's explanation. Light is not just a continuous wave, but also a stream of tiny packets of energy called photons. Each photon carries a specific amount of energy based only on its frequency, not its brightness. If the photon's energy is too low, it cannot free an electron, no matter how many photons you shine on the metal. But if the frequency is high enough, a single photon has enough punch to eject an electron instantly. This is why increasing brightness only increases the number of electrons released. It does not change the energy of each electron unless the color shifts toward higher frequencies. Once an electron absorbs enough energy from a photon, it escapes the metal surface with extra kinetic energy, which becomes measurable as electrical current. Scientists noticed that electrons were emitted with no time delay at all, showing that the photon interaction was immediate and direct. This discovery shattered the old classical view of light and confirmed the quantum nature of electromagnetic radiation. It also explains how modern solar cells work. Photons strike a semiconductor material, transfer their energy to electrons, and push them into motion to create electric current. If the photons don't have enough energy, meaning their wavelength is too long, they simply pass through without freeing electrons, which is why solar panels require certain wavelengths to operate efficiently. The photoelectric effect also powers technologies like light sensors, night vision devices, and scientific detectors that measure faint cosmic radiation. It even plays a crucial role in astrophysics, helping researchers understand how stars and galaxies emit high-energy photons that strip electrons from atoms in space. Einstein's explanation of the photoelectric effect earned him the Nobel Prize and marked the beginning of quantum physics, forever changing our understanding of light. What seems like a simple moment, a photon kicking out an electron, actually reveals a deeper truth about the universe. That energy, matter, and light all behave in ways that defy classical expectations, and that the smallest interactions can unlock the biggest ideas in science.